In this lesson, we're going to talk about complex numbers. Up until now in this course, we've been dealing with real numbers. In fact, you've probably only used real numbers in any math course so far in your life. Today, we will introduce you to complex numbers. A complex number is a number of the form a plus bi, where a and b are real numbers, and I squared equals -1. Since I squared equals -1, some people might think that I equals the square root of -1. Technically, this is not correct, but it is useful for many computations to think of it this way. The number I is called imaginary, and therefore sometimes complex numbers are referred to as having a real number component and an imaginary number component. Where do real numbers fit in here? Well, simply put, the set of real numbers is a subset of the set of complex numbers. Therefore, all real numbers are complex numbers. But a complex number is not necessarily a real number. So you might ask, well, how can a real number be a complex number? Imagine any real number, for instance, 7. A complex number is a number of the form a plus bi. Well, if we let a equal 7 and b equals 0, then a plus bi is equal to 7 plus 0i, which is just 7. So therefore, a real number is just a complex number with an imaginary component equal to 0. And the set of complex numbers is denoted by a C. We draw a C with a little line there. For a lot of complex numbers questions, we're going to use the quadratic formula as shown. And when we solve an equation involving complex numbers, we can't order our answers from least to greatest the way that we're used to, because imaginary numbers don't follow the same rules of less than or greater than that we're used to with real numbers. So we just list the solutions. And also remember, real numbers are complex numbers with an imaginary component of 0. So real numbers will be included in our solution set. So suppose we're asked to solve for x, where x squared plus 8x plus 20 is equal to 0. Well, we can't factor that, so we're going to use the quadratic formula. We have a equals 1, b equals 8, and c equals 20. So solving for x using the quadratic formula, we end up with 64 minus 80 underneath the square root symbol. Well, that equals -16. And so we end up with -8 plus or minus the square root of -16 over 2. Now, it's a property of square roots that the square root of AB is always equal to the square root of A times the square root of B. So by extension, we can say that the square root of 16 times -1 is equal to the square root of 16 times the square root of -1. So this square root of -16 that I've circled here, I can think of that as the square root of 16 times -1, which is the square root of 16 times the square root of -1. This root 16 that I've just circled is equal to 4, and this square root of -1, we're going to denote that I. So we can say that x is equal to -8 plus or minus 4i all over 2. We have a 2 in the denominator, and we'd like to be able to cross that out with the numerator if possible. We common factor out a 2 from the numerator, and we can cross these out, and we're left with x equals -4 plus or minus 2i. Okay, let's try again here. Solve for x, where x is an element of the complex numbers, and x to the 4 plus 4x cubed plus 4x squared equals 32x. Well, first thing we're going to do is set one side equal to 0, and then we're going to common factor. So we have a 4th degree polynomial. We common factor out the x, and we're left with a 3rd degree polynomial in the bracket. We're going to need to use the factor theorem to factor that. So we can try, the factor theorem is to some extent a trial and error process. We can plug a 1 in for x, but we get a non-zero value. We can plug a -1 in for x, we get a non-zero value. But when we plug a 2 in for x, we get a 0 value. that means x minus 2 is a factor. So we use synthetic division, and we divide x minus 2 from x cubed plus 4x squared plus 4x minus 32. And when we do that, we end up with the quadratic x squared plus 6x plus 16. So that means that our original fourth degree polynomial was really x times x minus 2 times x squared plus 6x plus 16. And that all equals 0. So it could be that x is 0, the first factor, or the second factor of x minus 2 is 0, or maybe the third factor of x squared plus 6x plus 16 is 0. Well, if the first factor said x was 0, the second one, if x minus 2 is 0, would mean x is 2. So we have two solutions so far. But that third one was x squared plus 6x plus 16 equaling 0 at the bottom of that slide. So if that's the case, then we use the quadratic formula because we can't factor. X would be negative 6 plus or minus the square root of 6 squared minus 4 times 1 times 16 all over 2. After doing some arithmetic, we get a negative 28 under the square root sign. So instead of saying the square root of negative 28, we can say the square root of 28 times negative 1. Well, that is the same as the square root of 28 times the square root of negative 1, which is what we've written here. Now, the square root of 28 can simplify to 2 root 7. So on our next slide, we say x could equal negative 6 plus or minus 2 root 7i all over 2. We'd like to be able to cancel out that 2 from the denominator. So we factor 2 out of the numerator. And in doing so, we are able to cross out the 2 with the 2. And our two complex solutions to the quadratic x squared plus 6x plus 16 equals 0 are x equals negative 3 plus or minus root 7 times I. Now, of course, we have x equaling 0 or x equaling 2 from earlier in the solution. So these are our 4 complex solutions. 2 of them are real and 2 of them are non-real. Let's solve this equation here. Okay, well, it's a fifth degree polynomial. One side equals 0. We'll common factor to start. And we're left with a fourth degree polynomial inside the bracket. We'll try the factor theorem. Plugging in a value of 1 for x into x to the 4 plus 2x cubed plus 8x plus 16 does not give us a value of 0, so x minus 1 is not a factor. Plugging in x value of negative 1 does not give 0. Plugging in an x value of 2 does not give 0. But plugging in an x value of negative 2 does give a 0. That means x plus 2 is a factor. So we use our synthetic division process. Since we're factoring out x plus 2, we put a negative 2 to the left. And our coefficients in our top line here are represent x to the 4 plus 2x cubed plus 0x squared plus 8x plus 16. We need to put a 0 here as a placeholder because there was no x squared term. Doing synthetic division, we get x cubed plus 0x squared plus 0x plus 8. Well, that is equal to x cubed plus 8. So what we have is x to the 4 plus 2x cubed plus 8x plus 16 equals x plus 2 times x cubed plus 8. But we know from sum of cubes that x cubed plus 8 is really equal to x plus 2 times x squared minus 2x plus 4. So we actually have two factors of x plus 2 in our overall fifth degree polynomial. Putting it all together, we get 3x times x plus 2 quantity squared times x squared minus 2x plus 4 is equal to 0. We can start by solving the factor x squared minus 2x plus 4 equaling 0. To do that, we're going to use the quadratic formula. All right, so plugging in an a value of 1, a b value of negative 2, and a c value of 4, we end up with negative 12 underneath the square root sign. That's the same as the square root of 12 times the square root of -1. Well, we know that the square root of 12 is equal to 2 root 3. So we can say that x is actually equal to 2 plus or minus 2 root 3 times I all over 2. We'd like to get rid of that 2 in the denominator if possible. We can do that by factoring 2 out of the numerator, canceling them out, and our x values from that part of the polynomial are x equaling 1 plus or minus root 3i. The other two factors, one was 3x. If we let 3x equal 0, then x is 0. We also had an x plus 2 quantity squared. If that equals 0, x is -2. So overall, our solutions are x equaling -2 or 0 or 1 plus or minus square root of 3 times I. And now let's try to solve this question. X to the 4 plus 8x squared plus 36 equals 0. Well, whenever we have a trinomial where our exponents on x are 4 and 2 and 0, and our lead term is a perfect square, x to the 4 is really just x squared squared, and our final term is a perfect square, 36 is 6 squared. When all of those things are all together in one, we can follow the following process. Take the square root, so to speak, of that lead term and the square root of that last term, and add them together and square that binomial. See what you get. Well, if we square x squared plus 6, we end up with x to the 4 plus 12x squared plus 36. So what we're going to do is we're going to say x to the 4 plus 8x squared plus 36 is equal to x to the 4 plus 12x squared plus 36 minus that extra 4x squared. Now you might wonder, why did we do this? Well, this x to the 4 plus 12x squared plus 36 is x squared plus 6 quantity squared. And this 4x squared is 2x quantity squared. And what we've done, what I've just shown here, is what's written here. And now what we've done is we've created a difference of squares. A squared minus b squared is equal to a minus b times a plus b. So we have x squared plus 6 minus 2x times x squared plus 6 plus 2x. Then we can reorder each of those trinomials so that we have them in descending powers of x. Now, since x to the 4 plus 8x squared plus 36 equals x squared minus 2x plus 6 times x squared plus 2x times plus 6, we can take our original expression, which was this, our original equation, which was this, and restate it as this. Now, what's the advantage to that? We've now broken it down into two different factors, and we can set each of those factors equal to 0. Neither of the factors factor further, but we can use the quadratic formula. So using the quadratic formula on setting the first trinomial equal to 0, we get a -20 underneath the square root sign, but we can call that root 20 times root -1. Root 20 is the same as 2 root 5, and the square root of -1 is the same as I. So then from here, we can factor 2 out of the numerator, cross that out with the 2 in the denominator, and we get two different solutions for x, 1 plus or minus root 5i. Similarly, that was what happens if you let x squared minus 2x plus 6 equals 0. But if you let x squared plus 2x plus 6 equals 0, similar process takes place. You use the quadratic formula, you get -20 under the square root sign. You change square root of -20 into square root of 20 times square root of -1. The square root of 20 is really 2 root 5. Square root of -1 is I. So factoring out the 2 from the numerator and from the denominator allows us to cross them out, and we get -1 plus or minus root 5i. So the two answers are from the previous slide, and the two answers from this side combine to give us our 4 answers to that 4th degree polynomial equation. And that's the end of this lesson on complex numbers.